Regarding the review that I plan to conduct for you, folks, should you be interested this Friday, period 5-6, the registrar sent me room in Floyd. Floyd's right over here next to Lee. You walk out here, you can see Floyd. I'll go check out the room to make sure it's accepted. Then I'll confirm such by announcing on Wednesday and posting such on our Sockeye Flats homepage. Now, today, we need you to become practitioners of the art of drawing pictures. Pictures of coordination complexes, particularly those which are octahedral, which means in the main, you need to be able to draw on a flat surface, your piece of paper, a reasonable image of this. We talked about this last time. The difficulties in drawing such stem from the fact that this is a three-dimensional object, but your drawing surface is two-dimensional. Now, if I hold the object in this spatial orientation, this, the top group, this, the central metal admirine, and this, the bottom group, the bottom ligand, top ligand, this, and this will be in the plane of our drawing surface. For me, the chalkboard, for you, your piece of paper. But these four in-plane ligands, which form a square, will be canted from a geometric orientation standpoint. That means these are going to be out in front of the drawing surface, at least that's what you must recognize, while these are behind the drawing surface. That's why when I draw these squares, I draw them canted. Now, on occasion, not surprising, students have difficulty when they first start wrestling with this issue. There's a game you can play if you so choose. I think you can afford a piece of paper, fold it in the shape of a square. Put a pencil through it, or a pen. This simulates your octahedron. 1, 2, 3, 4 corners of the square, top position, bottom position. And on this pencil that goes through the paper, pen, you can rotate this object. It's like this. We'll do this with pictures on the board, as well as with models, as well as with this, if you need to use this. You can label these four corners with the ligands. Ligand A, ligand B, ligand C, ligand D, whatever they might be. And you can rotate this as you see fit. If you need this in order to develop an ability to picture this from a two-dimensional drawing. So, use this if you need it. Isomers. Two types. Structural, stereo. You have discussed, at least most of you, structural isomers last week in discussion class. You will conclude the discussion of structural isomerism, or coordination complexes, tomorrow in discussion class as necessary, and then proceed from there. What I will tackle today is the stereochemical aspect of isomerism for coordination complexes, because these require modular simulation so you can see what the heck's going on. I have the wherewithal to arm our discussion staff folks with all the models they need. So I do the stereo stuff, they do the structural stuff. Now, cistrans. Or fernoxidal complex, where you have two sets of like ligands, facial and versus meridian. Those we talked about. The other category of stereoisomerism is that of optical or mirror image isomerism. I attempted to introduce you folks to this kind of stuff in Chemistry 2045 when you did the Tinker Toy experiment. Remember the Tinker Toy experiment? Assignment 6, you made models. When you made models, I called it the Tinker Toy experiment. Simple example. You like we've all done this. Show your left hand to a mirror. What do you see looking back at you? You see your left hand looking back at you? What do you see looking back at you? Maybe you haven't done this. Do it! Here's what you'll see looking back at you. See? These are mirror images of each other. Now the mirror is over here. Thumbs. Index finger, middle fingers, ring finger, little fingers. Palms facing forward. Question. Given that all material objects, provided they're not transparent, cast an image in a mirror. How do you find if the image that you see is the same as the object whose image was cast into the mirror? How do you find out it's the same thing? When you show this to a mirror and you see this looking back at you, are these the same thing? To find out if they're the same thing, you do a simple test that's called superimposability, which means you take one object and lay it over the other object and see if they are then geometrically identical. So I'll lay my left hand like this and my right hand on top of it, and I see at a glance they're not geometrically identical because immediately I see the thumb and little finger positions are different for the overlaid right hand, left hand objects. That leads to an important definition, one which you're going to hear all the time in organic class, called chiral. I decided to put this as part of our conversation, even though it's not in the notes. Chiral. If a species or an object, or the most common species we deal with in chemistry class is a molecule, okay, is not superimposable on its mirror image. Not superimposable. If they were superimposable, they'd be geometrically identical when I lay them upon each other. If a species is not superimposable on its mirror image, the species is chiral. That means it's optically active. That means the mirror image and the object whose mirror image was cast are in fact different. There are ways by which you can recognize the difference in these materials. It has to do with rotation of plane polarized light. I'm not really particularly interested in this physical property of an object and its mirror image, and such are not the same. You'll learn in organic class these are called enantiomers. I thought that name was important, now I write it down. You will learn if you study biochemistry, and I expect many of you will, that a principal difference between sugars and materials like wood fiber, cellulose, is that they're mirror images of each other. Well, does that have any significance in the life we live? We can ingest sugars and derive from such nutritional value. Termites can ingest sugars, but they don't get any nutritional value from them. Upshot, termites are not interested in eating sugars. What do they like to eat? Wood fibers. We can eat wood fibers, but we don't get any nutritional value from such, unlike the termites, which do. So it shows you example standpoint. That these chiral molecules, in fact, are not just physically different, they're also chemically different. And that's the test. That being superimposability. If you wish to know if an object and its mirror image are in fact the same or different, you superimpose them on each other. And if they're not geometrically identical after this test of superimposition, then they are in fact optical molecules and enantiomers in the language of organic class. Now, let's take a look at two species regarding question 2416 and the species which is discussed in the notes in the same area as question 2416. Let's start with this one. This is tris ethylene diamine cobalt 3, a complex ion. En represents ethylene diamine. We've introduced ourselves in this previously. And in these pictures of this complex, which is generally octahedral in shape, each of these loops represents an ethylene diamine molecule. Here, for example, is a nitrogen atom, CH2, CH2, NH2. NH2, CH2, CH2, NH2. But if I draw all that stuff in the picture is going to get awfully complex. So I instead simplify representation of an ethylene diamine chelating ligand with a loop. Like this. Is this chiral? Well, let's take a look at models. Never mind the fact that in one molecule, part of each loop is a green piece, whereas here, part of each loop is this kind of off-white part. They're supposed to be the same. Is this what I have on the board over there? Is this what I have on the board over there? Are these the same? That's the fun part. Well, we reminded you about the test. It's superimposability. Well, first let's see if these are mirror images of each other. All right? So here's my mirror. Here's a loop aiming right at the mirror. Here's a loop aiming right at the mirror. Notice the top loop. The top loop is canted toward you. And in generally that direction and that direction, or this versus this. How about the bottom loop? The bottom loops are canted toward me. One aiming rather that way and the other aiming rather that way. So do you agree these are mirror images of each other? If I show this to a mirror, I see this. The question is, are they the same? Let's overlay these loops. Oh, I can't overlay the loops because this thing's in the way. I can't overlay these loops because the bottom loops block each other. What happens now when I've overlaid the loops? This thing is not over here, overlaid with this. It's aiming that way. This is aiming this way. And the bottom loops are pointing in different directions. This is pointing this way. This is pointing this way. So guess what? This species is chiral. This is the object. This is his mirror image. Or if you prefer, this is the object and this is his mirror image. Who cares? They're mirror images of each other. And by superimposability, we have found out they are different. Therefore, that picture I have there on the board this right here is one of these, but it's not both of them. Which one is it? Well, look at this picture and recognize. Here's the Canton Square. All right? This ethylene diamine ring connects the top axial coordination position to this back left corner of my Canton Square. This ethylene diamine ring connects the bottom axial position to the left front corner of my Canton Square. And this ethylene diamine loop is not in the plane of the drawing surface at all, because this square is this way. So this loop is over here. This part of the loop is out in front of the drawing surface, and this part of the loop is behind the drawing surface. Now let's pick up one of these and see what we have. This is this. But we recognize, the picture on the board tells us, that the top ethylene diamine ring connects the axial position at top, that's this, with the left rear corner. This is connected to the to the left front corner. So this can't be this. That means this has got to be this. And there it is. Here's this loop, corresponding to this loop. Here is the loop, the ethylene diamine ring connecting the top axial position to the left rear corner of my Canton Square. And here's the bottom ethylene diamine ring connecting the bottom axial position to this left front corner of my Canton Square. Now, since you don't have the wherewithal of using these toys on the exam, but I will tell you this, for those of you who are going to proceed with further studies in chemistry, if as yet you have not purchased yourself an inexpensive model kit, do it. Invaluable in organic class. You got to make models of these things. And then you get yourself tuned up to this kind of stuff, and you'll know pretty soon what you're looking for when you see a picture on a flat surface. Model set. All right, let's look at what we see in the mirror. This loop is pointing at the mirror. This loop will now connect the top axial coordination position to this corner, which is away from the mirror, so that will be equivalent to this corner. So there's our mirror. Okay? So that's the other model. That's this one. Here's the loop, aiming at the mirror. Here's the top loop from the top axial coordination position now to the right rear corner of the Canton Square over here. And here's the one that connects the bottom axial position to the right front corner of the Canton Square. All right. How many of you have looked at bonus quiz 3? You think this might relate to bonus quiz 3 stuff? No. All right, now let's proceed with what you may find to be simpler geometric considerations, because these considerations, for the immediate moment, will deal with complexes containing monodensity labels. Question 2416. Stereoisomers for this thing. Diamino, diaco, dichloro, cobalt 2. Cobalt in the +2 oxidation state. You can recognize that at a glance because the ammonia molecule ligands and the water molecule ligands are molecules. They have no charge. Their oxidation states as entities are 0. But these are coordinated chloride ions. Oxidation state for each is -1. Makes this +2. Now with models, I'm going to change ammonia to green. Waters are purple. Chloride ions are light. Who cares? 2 G's, 2 B's, 2 W's. Now, one of the assignments placed to you by the statement of question 2416 is to sketch all the possible geometric isomers for this one. So I've started with pictures of the extreme opposite, not extreme opposites, but the extreme different cases. Where all like ligands are trans. Or, the extreme geometric opposite, all like ligands are cis, W, W, G, G, and P. And the models which I have are for all like ligands being cis. Because, if a species is chiral, optically active, because what we are reminding you about now is that included among all the geometric isomers for this thing is one isomer whose mirror image is different. It's the chiral isomer, the optically active isomer. Which one is it? If a species is chiral, it will always be of low or least symmetry. Which of these is of lower symmetry? You know what this word symmetry means? A highly symmetric species is a species which is simple or complicated geometrically. Simple or complicated? Simple. At least much more so than any asymmetric version of the species. If I'm a molecule composed of 3 atoms, never mind the body, just pay attention to my noggin, okay? Atom, bond, central atom. Am I now a symmetric molecule? What if my 2 peripheral atoms make a 90-degree angle with respect to the central atom, my noggin? Am I now more symmetric or less symmetric? Point. Symmetry plays a big role in determining species polarity. A linear species, 3 atoms, cannot possibly be polar if the peripheral atoms are identical, like CO2. But if I take a 3-atom species, like water, I know that water is polar, not because its 2 bonds are polar, because each of the carbon-oxygen bonds for CO2 are polar bonds. Why is water polar? Why is CO2 not polar? Because CO2 is perfectly symmetric. And the bond dipoles add together to become 0 at the center of the CO2 molecule. But for water, what kind of bond angle? About 105 degrees. Because non-bonding pair bonding pair repulsion shrink the bond angle relative to the perfect tetrahedral bond angle of 109.5 degrees. What if the water molecule had this geometry, would it even be more polar? As I shrink the bond angle, what's going to happen to that polarity? It's going to continue to increase. So, if we recognize that if a species, in this case a geometric isomer of this stuff, is going to be chiral, it's going to be the one of lowest symmetry, which means it's going to be this thing, where all like ligands are cis. Well, let's play a game. The game we're going to play first is to draw the mirror image of this. What are we going to see over here? Top bottom positions are immediately recognizable because when I cast the image of these into the mirror, their positions don't change at all. What do I see over here? And over here? Over here? No. Are these the same? Well, let's go back to this. Because when you are dealing with this issue on a piece of paper and you don't have models in your hand, you've got to have a gimmick to be used to find out if a molecule and its mirror image are truly different. So the gimmick I'm going to use is in my mind's eye for this, I'm going to take a hold of the top axial atom, the bottom axial atom, and I'm going to rotate this thing 180 degrees. Here's what I'm doing. I'm going to hold this thing. This one is this. Okay. I'm going to hold this thing, and I'm going to rotate it 180 degrees. Now when I rotate this 180 degrees, a simple reference point is this in-plane loop. Where's this in-plane loop going to aim when I rotate this 180 degrees? It's going to aim right at me, isn't it? Just like that. That's what we're going to do on the board. I'm going to take a hold of this thing, and I'm going to rotate it 180 degrees. These coordination positions remain the same. Where does this loop wind up? 180 degrees. Comes over here. Well, so far, that picture's like this picture. Aha! But let's look at this loop. Because when I rotate this tangent square 180 degrees, where does this position go? Winds up over here, doesn't it? So, this is now this. And this winds up over here. Hardly the same. Well, let's play the same game over here. Here's what I see when I take the mirror image of this. All right? Now, since we have recognized that this will be the optically active geometric molecule of this species, if it is optically active, I'm going to take, not this one this time, I'm going to take this one and rotate it. Doesn't make any difference which one you rotate. Again, I'm holding by the top G axially oriented ligand and the bottom P axially oriented ligand. If you need to number these positions to make it easier for yourself, do whatever it is makes it easy for you. Where's this P ligand going on? Here? Here? See, remember what I'm doing here. I'm rotating this 180 degrees. This one. Like this. Where's this line up? Here, 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 here. Here, here, here. Where's this lined up? 180 degrees, right? All right, now let's look at this picture. compared to that, where this is recognized by us to be the mirror image of this. But this is the same as this. All I did was to take this and let the wind blow it by 180 degrees. All right? G, G, P, P, W, 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 W. But look at what I got over here. The P ligand is behind the drawing surface. But over here, on the left side of the complex, the G ligand is behind the drawing surface, and the P ligand is out in front of the drawing surface. But here, the G ligand is out in front. So what have I found out? Chiral, yes or no? You betcha. I'll show you with models. Two models. Clearly in the complex that we're discussing. So each model consists of two purple ligands, two white ligands, two green ligands, and each set of like ligands are cis with respect to each other. Are these the same, or are they mirror images? How do we find out? Superimposition test. So let's hold the white ones this way and the white ones this way. Let's turn it over. How about that? These things are the same, right? Two greens, two whites, two greens, two whites, two purples, two purples. Now then, let's put down one model, doesn't make any difference which one. What I'm going to do now is I'm going to break and remake two bonds while maintaining all cis orientation of like ligands. Break, remake two bonds. Let's pick on this green one and this white one. See what we did? Just a second ago, the green one was here, the white one was here. Now the white one's here, the green one's there. But still, all cis are like ligands. What I have just done is to turn this thing into the mirror image of that. Let's find out. Here's my mirror. Whites. See the greens up top? Purples down below. Purple's projecting out toward you with the candid square. Green's projected toward me as part of the candid square. Do you agree these are mirror images of each other? Are they the same? Not now. Superimposability. White, 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 white. Green, green, purple, purple, but that's what we saw on the board. Interesting, isn't it? Interesting how a mirror image of an object can in fact be different from the object itself. Just like your left hand and your right hand. And all sorts of objects with which we are familiar show this kind of characteristic. It's called chiral. Interesting. Now, just for a little bit more practice, take a look, if you will, at questions 24, 17, well, we already did 17, 18 and 19. 17 is the facial meridional issue. Let's look at 18 and 19. Notice for 18, I again have a cobalt cobalt complex, octahedral, the +2 oxidation state for cobalt. Cobalt +2 oxidation state, octahedral complex. Same types of ligands throughout. Ammonia, water, chloride. But I've gone from 2 ammonia ligands to 3 ammonia ligands and reduced the number of water molecule ligands from 2 to 1. Your assignment is to draw as many geometric isomers for this system as you can and answer the question, are any of these geometric isomers chiral? Well, before we wrestle with the question, how many geometric isomers, let's go back to this cobalt thing. This thing. We've shown you the least symmetric geometric isomer for this cobalt complex, where all like ligands are cis to each other, and that one's optically active. And we also showed you, although I erased it, the most symmetric geometric isomer for that cobalt complex, where all like ligands were trans to each other. How many more geometric isomers? I agree. Are we seeing this? Well, they all share the same geometric feature of having like ligands cis. Well, therefore, in any other geometric isomer other than the all trans, we've got to have a mix of cis and trans. Do you agree with that? We looked at the all cis, we looked at the all trans, so let's make 2 phosphoruses. Purple. Let's make purple trans. Well then, and put a green one here. What position, what ligand, G or W, since the purples are all used up, G or W has got to be here for this to be different from any of those which we've looked at so far. Well, I can put a W there. Okay. Now then, if I put G here, that's going to force W here. And that will be all trans for like ligands. I've seen that already. So the only way I can draw something different is to have the 2 light purple ligands trans and the remaining sets of ligands cis to each other. GG 90-degree angle, WW 90-degree angle, purple, middle, central atom, purple, 180-degree angle. So I hope this is causing you to realize that the remaining 2 geometric isomers for this will be the G's trans, and D and WW cis, and the last one is W trans, and G and D cis. That's it. So that leads me to a question. Is this a more symmetric or less symmetric species than G2, B2, W2? Will this have more isomeric variation, the same degree of isomeric variation, or a lesser degree of isomeric variation than what we've got now? We haven't had a vote in a while. Let's have a vote. That one is of lower symmetry than this, so that one will have at least as many, if not more, eyes looking around. I want you to look at me, damn it. If there's any cheating in this election, I do it. How many vote that's more symmetric? A lot of people hesitate to vote. How many vote that's the same degree of symmetry as this? You don't want to vote, do you? We had a lot of non-voters. I'm going to review my tape. You'll start off with minus 10,000 on the final. All right, minus 20,000. Well, I'm going to leave you with that question. We'll pick it up from this point next time. But, do remind me. See this? This is a substituted ammonia liquid. Instead of 3 hydrogen atoms, I have a hydrogen atom, a methyl group, and a chlorine. Is this chiral? Secondly, there's a word which relates to stereoisomeric character. I want you to look up this word and know what it means when we meet for Wednesday's last official conversation. Diastereomer.